What's up, everybody? Welcome to what I think is the 8th, maybe the 9th lecture. I have to look into that in a minute. But welcome to the continuation of your calc lectures. Today's lecture is going to be over section 2.2 and 2.3. Really, we're just going to talk about these differentiation formulas. Because you know that limit definition of the derivative, it's great and everything, but after a while it gets to be tedious. As a result, it's nice to know how differentiation works on particular types of functions. That way you don't have to keep repeating this process over and over and over again. For that reason, we have section 2.2, 2.3, 2.4, and I think 2.5 touches on it as well. And these are all the tricks of the trade, the patterns that occur that are going to be ubiquitous enough that you can just take advantage of them and not have to keep applying that limit definition. So to start off with, we're going to go through, like I said, just these. The first one, probably the most obvious, is that the derivative of a constant is just going to be 0. And this makes sense when you think about the tangent line, right? Well, the derivative is a line, or is the measure of the slope of a line tangent to a function at a particular point. Well, if your particular function is just a constant, so y equal to a constant, then that thing has no slope, right? That is 0 times x plus a constant. So your slope is 0. And every tangent line is going to be identical to just that constant value, right? For that reason, the tangent line has a slope of 0. And we can say, just from an intuitive perspective, that yeah, of course, the derivative of a constant is going to be 0. This tangent line has a slope of 0. And this makes sense. If you even go back to rise over run, that line has a slope of 0 everywhere. But moving on, the derivative of the constant multiple of a function, so c times f of x, is just equal to c times the derivative of that function. So in other words, you could just pull that constant multiple outside, don't worry about it. Take the derivative and then multiply your constant through, which is convenient sometimes. For example, let's say you had 2x squared. The derivative of that is 4x. And the way to see that is by applying this rule, and what in a second we're going to see to be the simple power rule. Now, the next rule to talk about is the sum and difference rule. The derivative of the sum or difference of two functions, so the derivative of f of x plus or minus g of x, is equal to the derivative of f of x plus or minus the derivative of g of x. So you can apply the derivative to each individual part, which we've already seen through some of the previous lectures. Then we get into what's called the quotient rule. The quotient rule, when talking about the derivatives, is usually the thing that trips people up the most, because usually we try to memorize it, and after a few more lectures, you're not going to really need to, because the quotient rule actually comes from what's called the power, or the product rule. Sorry, that was just evading me for some reason. It comes from what's called the product rule and the chain rule. And there's an application possibly of the power rule there as well. But the quotient rule says that if you have f divided by g, and you take the derivative of that, then that's going to be equal to g times f primed plus f times g primed, all divided by g squared. Now notice I'm using some new language here. I'm not saying the derivative of f, but that is what that means, right? Think back to that last lecture. At the end of it, I pointed out there's a bunch of new notation. And one of the things I showed was this prime notation, where instead of writing d dx of f of x, you could instead write just f prime of x. And those two statements are equivalent, right? Well, that's what this is taking advantage of. This is just condensing the notation because, man, that would suck to write d dx all throughout that. It just gets messy looking, right? Looks terrifying. So we like to use this prime notation in cases like this. Having said that, the next rule to talk about is the derivative of the product of two functions, d dx of f times g of x. Well, that thing's going to come out to be equal to g times f prime of x plus g prime times f of x. So notice in that first term, we're only taking the derivative of f, and in the second term, we're only taking the derivative of g. But we are taking the derivative of each function, it's just at different times, right? So d dx of f of x times g of x is equal to g of x times f prime of x plus g prime of x times f of x. Having said that, the next one to talk about is what's called the simple power rule. I grew up hearing it called the power rule. Your textbook likes to call it the simple power rule, because there's another generalization that can be made using what's called the chain rule, which we'll get to in another, I think, 2 lectures, maybe the next lecture. No, it is another 2 lectures. But the simple power rule says that if you have x raised to any power other than 0, so x raised to any power other than 0 is equal to that power times x raised to that power minus 1. So x squared, according to this power rule, is going to be 2 times x raised to 2 minus 1, or just x. So x squared, the derivative of that, is equal to 2x. And that's how I was able to do that derivative just a second ago about 2 times x squared being equal to 4x. Now, having said that, there is one function in particular that mathematicians love. E. E raised to the x, right? We love that thing. And the reason why is because, well, it is its own derivative, which is, phenomenal. We love this thing because we don't have to do much to it. And it says something very particular about it, that as you move along that function, whatever the value of y is the slope of your function, which means it's measuring its own slope, which is kind of a cool fact. There's going to be another function that we're going to see later down the road whose area does something special. Well, the area under its tangent lines do something special is what I should say. But that's after midterm. Having said that, I'm going to erase these. We're going to use a few of them on a couple problems just to kind of get the hang of how we're going to use them. All right, so for this first example, let's check out this derivative. So we're given this crazy polynomial. It's 7x cubed plus x squared minus pi x plus 5. We need to take the derivative of that polynomial. Okay. Well, we could apply the sum and difference rule right away here and take the derivative of each individual term. So we could rewrite it to look like this. This thing is equal to d dx of 7x cubed plus d dx of x squared minus d dx of pi x plus d dx of 5. Okay. Well, now that we have it broken up like this, there's two derivatives in particular that jump right out at me. Two of them because we just talked about them, and these are rules that we can apply right away. And then the other two, we have to do some rearranging, but we'll be able to solve them in just a second. So the two that we can solve right now is this derivative here and this derivative here. This derivative right here, we just have to apply what's called the constant rule, right? Because the derivative of a constant is 0. So that one, that's easy. That's a given. So we can apply that derivative of a constant rule. Now, for this term here, well, this is the simple power rule, right? Here we're saying n is equal to 2. So if we're going to apply the simple power rule, we have x to the n, the derivative of x to the n. Let me write it down actually. d dx of x to the n is equal to nx to the n minus 1, right? Well, in our case, n is equal to 2. So we can rewrite this as 2 times x to the 2 minus 1. Well, 2 minus 1 is just 1. So we can leave it as it is from there. Now, for these next two terms, we can use the multiple rule, right? The constant multiple rule. We can pull out this 7, and we can pull out this pi. To get that these are equal to 7 times d dx of x cubed, and this is equal to pi times d dx of x. Well, from here, this is a simple power rule again, isn't it? And this, well, this is a simple power rule in hiding, right? Because in this term right here, the n is equal to 1. This is just x to the first power. Do not confuse it for x to the 0th power. Anything to the 0th power is always 1, right? So this here is x to the first power. So when we apply the power rule, the simple power rule here, we're going to have 1 times x to the 0th power, or just 1. So all that's going to come out to be pi times 1, or just pi, to x, and then this is going to be 7 times whatever this derivative is here. Well, this derivative here is going to come out to be 3x squared, right? So now we can simplify and rewrite everything and say that d dx of 7x cubed plus x squared minus pi x plus 5 is equal to 7 times 3 is 21, x squared plus 2x minus pi. And that, ladies and gentlemen, is the derivative of our original polynomial here. So take a second to absorb this. Pause the video if you need, but I will be erasing this and moving on to another question now. Okay, so for this first example, we need to do some MacGyvering here. Or for the second example, not the first. We just did the first. This is the second. What am I thinking? Anyhow, we need to do some MacGyvering on this example. What we need to do is we need to recognize that there are actually two functions hidden here. We have f of x equal to x squared, and we have g of x equal to e to the x. Moreover, we need to remember that we know d dx of f of x times g of x is equal to g of x times d dx of f of x plus f of x times d dx of g of x. Now don't be confused. A minute ago I wrote f primed and g primed. This again is the same thing, right? To say d dx of f of x is the same thing as to say f primed of x. Okay. Now here is going to be helpful to break this problem up. Since we've identified what f and we've identified what g are, why don't we go ahead and take both of their derivatives? This tells us that f primed of x is going to be equal to 2x. That's by the simple power rule. And g primed of x is just going to be e to the x. That's because d dx of e to the x is just e to the x. So the derivative of e to the x is just e to the x. Now, from here, we can put it all back together, right? From here we can say, well, this thing is going to be equal to g of x times f primed of x plus f of x times g primed of x. Well, g of x, we said, is equal to e to the x. F primed of x, we said, is equal to 2x. F of x is equal to x squared. And g primed of x is equal to e to the x. So we could do some rearranging now and rewrite this as 2x plus x squared, that quantity times e to the x. And we could also pull out an x if we wanted to say that this is equal to 2 plus x times x e to the x, if we wanted to simplify it further. We don't have to. This is just if we wanted to. Kind of a practice of some algebra here for us. So just as a general tip, when it comes to the product rule and the quotient rule, I personally find it easier to start by rewriting the derivative formula or the derivative rule in particular that I know what you need. Then identifying what each of the individual functions are. And then going one step further and saying, well, what's their derivatives? Because I know I'm going to need those, right? Then from there, it's just a matter of pattern recognition, right? Of saying, well, I know what f of x is, fill in the blanks. I know what g of x is, again, fill in those blanks, so forth and so on, and piecing it all back together according to that formula. That's the approach that I generally take. Having said that, let's look at one last example. All right, so for this final example, we want to take the derivative of this rational function, of this quotient. And it's the derivative of the quantity x minus 1 divided by the quantity x cubed plus 3x minus 4. So this is, in fact, a plus sign here, in case that is not clear while you're watching YouTube. So we've got the derivative of the quantity x minus 1 divided by the quantity x cubed plus 3x minus 4. This looks like it's going to suck, but it's not. I promise it won't. Because the first thing we can do is we can stop and remember, oh, wait a minute. I know the quotient rule. The quotient rule tells me that d dx of f of x over g of x is equal to, well, man, I forgot what that rule is. How am I going to remember it? I'm glad you asked. There is a nice mnemonic that pretty much everyone gets taught at some point in calculus when talking about the quotient rule. That mnemonic is low d high minus high d low divided by the square of what's below. So low d high minus high d low divided by the square of what's below. And what it's saying is low, g of x, times d high, so the derivative of f of x, minus high, so f of x, times d low, so the derivative of g of x, or g prime of x, right, divided by the square of what's below, that's g of x, that quantity squared. Cool. It's a great little mnemonic. Now I know what my f and my g's are, right? F of x is going to be whatever is in the numerator. Well, in this case, what's in the numerator is x minus 1. And the derivative of that thing, f prime of x, well, that's just equal to 1. Meanwhile, g of x, that's going to be equal to x cubed plus 3x minus 4. X cubed plus 3x minus 4. And its derivative is going to be 3x squared plus the derivative of 3x, which is just 3, minus the derivative of 4, which is just 0, so we don't need to worry about it. Now, to put all of this back together, we have that this is going to come out to be g of x times f prime of x minus f of x times g prime of x, all divided by g of x squared. Okay, so now we can put all of this back together. So starting off with g of x, that is x cubed plus 3x minus 4 times f prime of x. Well, f prime of x was just 1. So 1 times this does nothing, just leaves this. So why don't we just leave it as it is? Don't worry about it anymore. Now, moving on to the next part, we have f of x, that was x minus 1 times g prime of x, which is 3x squared plus 3, and all of this divided by x cubed plus 3x minus 4, that quantity squared. Now, of course, from here, we can go through and simplify this. I can honestly say I do not know if WebAssign will expect you to have your answers simplified or not. I don't know. I have no wild idea. I know on an exam, this is what I'm going to be looking for. You don't necessarily have to simplify it beyond this. On your homework, I do not know, but you also have 100 attempts when it comes to your homework. So if you get to this and you're like, it's not taking my answer, go ahead and simplify it. See if it takes it then. It's not going to hurt anything. Because obviously here, we can multiply these two quantities together. We're going to get an x cubed and have some cancellations across the top, and a few things might drop out. You might find that we have another cancellation between the numerator and the denominator. I don't know. But on an exam, this will be sufficient. Having said that, that is all I have for y'all today. I will see y'all in the next lecture. In the next lecture, we're going to go over 2.4, which, if I remember correctly, is all about trig functions and their derivatives. So, if right now you hear the word trig and it terrifies you, take a deep breath. You're okay. It's not going to hurt, I promise. Or at least, I'm not going to make it hurt intentionally. I'm going to do everything I can to make this material easy and digestible. However, that anxiety is a pretty good sign that take a step back, go review those trig notes that I left for y'all on Blackboard. I believe it's Nancy Pye that had a great trig review, as does 312 Brown or whatever it is. I can't remember his name anymore. But as does one of the other YouTube channels, and obviously Khan does as well. So, if when I say that 2.4 covers the calculus of trig, that terrifies you, you're okay. It's okay. This is at your pace. Go back, review that stuff. Come back to the next video. You'll be good, I promise. Having said that, that is all I have for y'all, so I will let y'all go. Have a good one, everybody.